Hey there, you incredible knowledge seeker, and welcome back to the Deep Dive.
It's great to be back.
If you're anything like us, you've probably spent hours, maybe too many hours, lost in the fascinating details of how the world works. It happens.
Oh, definitely. Down the rabbit hole.
Exactly. But sometimes, it's the really big questions that hit the hardest. Like, what's actually fundamental?
That's the big one, isn't it?
It really is. Hit that like button if you've ever found yourself staring at the ceiling, pondering that one. And definitely subscribe so you don't miss our next descent into the unknown.
Please do.
Today, we're plunging headfirst into this amazing treasure trove of thought called What is Fundamental? It's part of the Frontiers collection.
Right. And this book, it sprang from the Foundational Questions Institute, FQXi. They ran this essay contest, and the book collects some of the most fascinating responses.
It's like a backstage pass to the universe's deepest secrets. Seriously.
That's a good way to put it. And what makes this collection so captivating is just the sheer diversity of voices tackling this giant of a question. Totally. You've got physicists, you've got philosophers, all coming at it from different angles. They're locking horns intellectually, of course.
Of course. No actual headbutting involved, we assume.
You hope not. And spoiler alert, there's no single easy answer just waiting for you at the end.
No neat little dough on this one.
Not at all. Instead, what you get is this dazzling spectrum of ideas. It really makes you rethink what it even means for something to be truly fundamental.
Exactly. So buckle up, because our mission today, yours and ours, is to navigate this whole intellectual landscape together.
Let's do it.
We're going to try and pull out the most mind-blowing insights from these essays, maybe connect some dots in ways you might not have expected.
And hopefully leave you with a deeper appreciation for the sheer mystery at the heart of reality.
Couldn't have said it better. Okay, let's dive in.
Okay. A perfect place to start, I think, is this realization that our understanding of fundamental isn't. Well, it's not set in stone.
Right, it changes.
Emily Adlam makes this point really compellingly. She argues that what we consider fundamental actually shifts as science progresses.
Yeah, think about it, the atom, right? For ages, that was it. The indivisible bedrock of matter.
The final layer. Until it wasn't.
Until we split it wide open.
Exactly. Or, think about time before Einstein. Absolute time, absolute simultaneity that seemed utterly fundamental.
Until relativity came along and showed us it's, well, relative. Depends on your frame of reference.
So what was once the final answer suddenly becomes just another question that needs explaining.
It's like the goalposts keep moving. Edlin points out this history suggests maybe we're asking the wrong thing or in the wrong way.
Instead of always digging down looking for smaller and smaller building blocks.
The sort of Lego brick model of reality.
Right. Maybe we should be asking, what are the fundamental principles or regularities that govern everything?
That's interesting. So not what is fundamental, but why are things so regular?
Precisely. Adlam proposes this shift. Instead of explaining things via components, maybe the real mystery is understanding the regularities themselves. Why are there consistent rules? Why can we predict anything at all?
That regularity itself, that could be the fundamental thing.
It could be. That's the provocative idea. Why this reliable structure to reality?
And it gets even more meta, right? Because she hints that maybe our whole definition of what counts as a good explanation needs an upgrade.
Yeah, we're so used to explaining by breaking things down. Reductionism.
Explain the clock by showing the gears.
Exactly. But maybe a truly fundamental understanding needs a totally different kind of framework. It's like trying to understand a symphony by just analyzing the frequency of each individual note.
You miss the music. You miss the structure, the harmony, the whole point.
You miss the whole composition. It's a great analogy.
Okay, so that's Adlam questioning the stability and the method of finding the fundamental.
Now, shifting gears a bit, Matthew Leifer comes in and challenges the whole idea of a single top-dog fundamental discipline.
Like physics being the king of the hill.
Exactly. Physics reigning supreme over chemistry, biology, sociology, everything. His view was partly shaped by the science wars debates back in the day.
Oh, yeah, I remember those. Lots of arguments about objectivity and social construction.
Right. And Leifer developed a healthy skepticism towards the idea that everything ultimately just boils down to physics, that concept known as physicalism.
Which is basically the idea that all facts are ultimately physical facts.
That's the gist of it. So Leifer saw these clashes and questioned this neat hierarchy, physics at the very top.
So what does he propose instead?
He offers this really captivating idea, knowledge as a scale-free network.
Okay, unpack that. Scale-free network.
Think about the World Wide Web, or Wikipedia. You have these incredibly connected hubs, really popular pages or sites with tons of links.
Right, like central nodes.
But crucially, no single web page or entry is inherently more fundamental than any other. They're all just vital parts of the whole web.
Ah, I see. So it's not a pyramid, it's a network.
Exactly. And Leifer sees different disciplines, physics, sociology, biology, art history, whatever, as these major hubs in this vast network of knowledge. Each one is crucial for understanding different facets of reality.
So if you're deep inside the physics hub,
It's natural to see physics as the key to everything. Your connections mainly lead to other physics concepts.
but someone in the sociology hub might see social structures as the real driving force, because that's their central node.
Precisely. There's no objectively highest point in this network. It explains why brilliant people in different fields can have such different views on what's fundamental. It depends on where you're standing in the network.
So that whole argument about which field is most fundamental just kind of dissolves.
In Leifer's view, yes, it's not a hierarchy, it's a web, which makes a lot of sense, actually.
It does. It feels less territorial.
And he connects this to a sort of pragmatist view of truth. What works, what's useful for our understanding and prediction, that's what we tend to call true.
So it's less about some ultimate capital T truth out there,
What philosophers call ontology, the study of what is.
and more about how we build and structure our knowledge.
Exactly. More epistemology, the study of knowledge itself. It's about the map, not necessarily the territory in some absolute sense.
Okay, that's a really different perspective. Now, Alyssa Nee brings another angle, right? She talks about the politics of fundamentality.
Yes, this is fascinating. Nee examines how physics historically got this top billing, this status of being the fundamental science.
And she says it's largely down to two big claims physics made for itself.
That's right. Claims of what she calls constitutive completeness and causal completeness. We should probably unpack those a bit.
Yeah, let's do that. Constitutive completeness. Sounds like construction.
Pretty much. It's the idea that everything in the universe is ultimately built from a set of fundamental physical building blocks, like the Lego analogy again.
Everything's made of atoms, which are made of quarks and electrons, et cetera, bottom up.
Exactly. Physics historically championed this view, but Nee points out that even within physics, this simple building block model is being seriously revised.
How so?
Well, the way non-fundamental things arise from more basic ones, emergence, can be way more complex than just stacking blocks. Think about, water emerging from hydrogen and oxygen.
Right. Wetness isn't a property of a single H2O molecule, is it? It emerges from how lots of them interact.
Exactly. It's not just simple assembly. New properties appear that weren't obvious in the parts. Less Lego, more complex chemistry.
Okay, so that's constitutive completeness being questioned. What about causal completeness?
Causal completeness is the idea that all events, all effects, can ultimately be explained by physical causes. Physical laws govern everything that happens.
And the argument for that is basically physics track record.
Largely, yes. Physics has successfully explained so much, from atoms to stars, so it's tempting to think, well, it must be able to explain everything eventually. It's an inductive argument. It worked here and here and here, so it'll probably work everywhere.
But Nee throws some cold water on that, too.
She does. She asks, are our actual physical theories really complete in either sense? Can the standard model truly account for consciousness, for example? Or even things within physics, like dark matter?
Good point. We see the effects of dark matter, its gravitational pull, but we haven't actually found the particle or explained what it is within our current fundamental theory.
Precisely. So if this idea of completeness is maybe a bit shaky as the basis for claiming fundamentality, what's the alternative?
Yeah, what does Nee suggest instead?
She introduces this concept of maximality. This is really interesting. She argues that maybe a more relevant way to think about fundamentality in science is about a theory's ability to be unified and to just outperform its rivals.
Outperform them how?
In terms of its scope, what it covers, its accuracy, and its precision, but for a specific target class of phenomena.
Okay, so not necessarily explaining everything, but being the best possible explanation for its particular domain.
Exactly. Think about, say, the BCS theory of superconductivity. It's considered the fundamental theory of superconductivity, not because it explains the Big Bang, but because it's the most unified, accurate, precise explanation for that specific phenomenon.
Or like Darwin's theory of evolution for biology.
Yeah.
Fundamental within its domain.
Right. And Nee argues that a truly fundamental theory, in the grandest sense, would be a unified theory that achieves this maximality across all phenomena. It's a more pragmatic, maybe even achievable goal than absolute completeness.
That feels more grounded.
She also touches on the cultural value we place on fundamental research, echoing physicist Victor Weisskopf.
Oh, right. The idea that basic science is the wellspring, the source of future innovation, even if you can't see the immediate application.
Exactly. But then, highlighting the politics part, she shares this anecdote about a research funding exercise she does with students.
What happens?
When they have a limited budget to allocate, the really deep fundamental physics proposals, cosmology, particle physics, often get pushed aside.
In favor of?
Projects with more obvious, immediate societal benefits. Curing diseases, tackling climate change, things like that.
Wow. That really forces you to think about how we, as a society, actually value different kinds of knowledge, doesn't it?
It absolutely does. How do we justify searching for the Higgs boson when that money could fund, say, Alzheimer's research? It's a tough question about priorities and the perceived connection or lack thereof between fundamental questions and real-world problems.
And one last point from Ni Kitavi. She reminds us that physics often just assumes this basic, eternal stuff exists, right?
Yeah, since the scientific revolution, there's often been this implicit assumption. There's some fundamental, unchanging physical substance. The laws just describe how this stuff is arranged and interacts.
But it doesn't really ask where this stuff came from. Or why it has the properties it does.
Exactly. It's like having the perfect rules for chess, but no explanation for why the board and pieces exist in the first place.
Okay, so that's a lot to chew on. Now, Dean Rickles dives even deeper into this sort of ingrained assumption, this fundamentalist intuition.
Yeah, he talks about this deep-seated feeling most of us have, that there just has to be an end to the questioning. You can't just keep asking what's it made of forever.
The infinite regress problem. Turtles all the way down.
Right. Rickles points out that many philosophers operate with this dichotomy. Either there's a final bottom layer, or it's this endless chain. And the infinite regress is often dismissed as, well, problematic, maybe even incoherent.
Like existence would never get started if it depended on an infinite chain before it.
Something like that. It's like trying to reach the end of a rainbow. You just keep going.
But Rickles brings in a counterpoint, doesn't he, from ancient philosophy?
He does. He talks about the Parmenidean approach. Parmenides had this radical idea that fundamental reality wasn't tiny bits, but this single, indivisible, unchanging, eternal whole.
Whoa. So starting from the complete opposite end.
Totally. Everything else we perceive, space, time, change, matter, is somehow derived from this fundamental oneness. It's like starting with the finished painting and trying to understand the brushstrokes instead of starting with the paints and building up.
That completely flips the script on what fundamental even looks like.
It does. So you have these two ancient opposing strategies, the atomists building up from simple components, and the Parmenideans deriving everything from a complex whole.
And Rickles connects this to modern physics.
He does through the concept of duality. He suggests these approaches might not be enemies, but maybe complementary ways of seeing the same underlying reality.
Like two sides of the same coin.
Kind of. He mentions the quarkist versus bootstrapper debates in particle physics as a modern echo. Do you find the fundamental by smashing things smaller? Quarkist atomist. Or by finding a self-consistent web of relationships where everything implies everything else? Bootstrapper Parmenidean.
That's fascinating. And he also mentions attempts to unify physics that aren't about finding the smallest thing.
Right, like Einstein's lifelong quest for a unified field theory. The goal there was to derive particles and forces from the geometry of space-time itself.
So the fundamental layer would be space-time geometry, kind of at the top of the hierarchy.
In a sense, yes. With particles emerging from wrinkles or structures in that geometry, it's a total reversal of the usual bottom-up picture. Really mind-bending stuff.
Okay, so the picture's getting way more complex than just digging down. Marx again then looks at the diversity within physics itself, right?
Exactly. He points out that while, yes, many physicists might point to the Standard Model as our current best bet for a fundamental theory.
With the hope of finding a supermodel or a theory of everything eventually.
Right, but there's actually significant debate and disagreement even within the field. The Standard Model is amazing, but it's incomplete.
Doesn't include gravity, doesn't explain dark matter or dark energy.
Which make up 95% of the universe, so clearly not the final word.
And this is where emergence comes back in strongly.
Crucially, Seguin discusses how many argue against a single ultimate fundamental level. They suggest that equally fundamental concepts and theories can exist at different levels of description.
Like thermodynamics again. the laws governing heat and energy in bulk systems.
Perfect example. Those laws emerge from the chaos of countless atoms, but they have their own fundamental principles. They aren't just simple consequences of atomic motion, they have their own logic. More is different, as physicist Phil Anderson famously put it.
And Seguin mentions that some people even push this further, suggesting higher levels could be fundamental.
Yeah, potentially even consciousness itself, which really turns the traditional bottom-up view completely on its head.
Whoa. And he makes a really important distinction here, doesn't he, between two kinds of fundamentality.
Yes, this is key. Epistemological fundamentality versus ontological fundamentality.
Okay, break those down.
Epistemological is about our knowledge, our theories, what's fundamental to our understanding. Ontological is about the world itself, independent of us, what is fundamentally real out there.
So a theory could be fundamental to how we explain things, without necessarily meaning the things in that theory are the ultimate reality.
Precisely. And Seguin shares this amazing anecdote from an FQXi conference.
The consciousness one.
That's the one. A panel was discussing consciousness, and apparently the consensus tilted towards the idea that consciousness might actually be more fundamental than space, time, and matter.
That is radical. Seriously radical.
It is. And he connects this to Frank Jackson's famous thought experiment, Mary the color scientist.
Mary in the black and white room. She knows all the physics of color vision.
Every physical fact, how light hits the retina, how signals travel to the brain, everything.
But she's never actually seen color. Then one day, she walks out and sees a red rose.
Does she learn something new? Jackson argued, yes, she learns what it's like to see red.
Which implies that subjective conscious experiences, qualia, as philosophers call them, are real aspects of the world, not captured by physics alone.
Making them, perhaps, ontologically fundamental in some way.
And then there's Descartes, right? I think, therefore I am.
Seguin brings that up too. Our own conscious awareness is arguably the one thing we know with absolute certainty. From an epistemological standpoint, it's hard to get more fundamental than that.
Okay, consciousness as potentially fundamental. That sets the stage nicely for Marcus Miller.
Oh, yes. Miller takes us somewhere truly unexpected. He basically proposes we should reverse the arrow of fundamentality.
Reverse the arrow. What does that mean?
Well, the standard scientific picture, the orthodox view is material universe first, evolving according to physical laws. Observers, consciousness, life. That all emerges much later from complexity. Physics is the base.
Makes sense. That's how we usually think about it.
But Miller suggests, what if the self, our conscious experience, is actually more fundamental than the external world, in a very specific mathematical sense?
How on earth would that work?
He uses this analogy from a branch of math called non-commutative geometry. It's pretty abstract, but the gist is, sometimes you can reconstruct a geometric space entirely from the algebra of functions defined on that space.
So the math description becomes, in a way, more basic than the shape itself.
Kind of, yeah. And he hints that maybe quantum theory, with its abstract mathematical structure, might be more fundamental than space-time. Space-time itself could emerge from the quantum rules.
Wow, okay. So observers first, world second.
In a specific sense. He acknowledges the standard view works incredibly well in its domain, everyday life, predicting planets, building bridges, small universe, limited tech, ignoring quantum weirdness, mostly.
But maybe it breaks down at the extremes.
That's his argument. When you consider the whole universe, or advanced AI, or the full implications of quantum theory, maybe the cracks start to show.
So what does he propose instead of physical laws?
He introduces this concept called algorithmic probability. Basically, it favors simpler, more compressible explanations or patterns in data.
Simpler is better. Occam's razor on steroids.
Sort of. He proposes a postulate 1. An observer's experience, their sequence of conscious states, is governed by this algorithmic probability distribution. No external world needed in the postulate itself.
Just the observer's experience stream.
Yes. And from this, he derives things like the principle of persistent regularities. If you keep seeing a pattern, algorithmic probability says you'll likely keep seeing it.
Which sounds like induction, how we expect the sun to rise.
Exactly, but derived from this observer-centric starting point. And interestingly, this framework might offer a way out of the bizarre Boltzmann brain problem.
The idea that random fluctuations could just pop a thinking brain into existence with false memories, which seems statistically more likely than our ordered universe.
Right. Miller's framework heavily disfavors such random, unexplainable complexity appearing out of nowhere. It prefers compressible, patterned experiences.
And then there's his theorem, too.
Yeah, this is the kicker. It suggests that observers governed by algorithmic probability will most likely find themselves experiencing states that look like they are part of a larger, computable, probabilistic process.
In other words, an external world.
Exactly. An apparent external world with consistent laws emerges as the most probable type of experience for an observer, simply because such worlds are algorithmically simpler than pure chaos.
So the external world is an emergent illusion, but a very persistent and probable one.
That's one way to read it. But Miller stresses this doesn't invalidate normal causal explanations within that emergent world. If you see a meteor hit the Earth, it's still perfectly fine to say the meteor caused the crater in your experience.
It just adds this deeper, observer-centric layer underneath it all.
Precisely. It's a compatible alternative, offering a reason why there appears to be an external world with laws in the first place. Wild stuff.
Absolutely wild. Okay, from the observer back to the brain. Tejinder P. Singh has this really elegant idea, the thing law.
Yes, this is quite poetic, actually. He suggests that the dynamic neural pathways in our brain have this dual nature.
Dual nature, how so?
They are physical things, neurons, synapses, electrical signals, but our consciousness also interprets or experiences them as abstract laws. Our thoughts, ideas, feelings, even our understanding of mathematical or physical laws.
So the same neural firing pattern is both a physical event and the subjective experience of, say, understanding a memory, a concept, a word, a thought, or a feeling.
That's the core idea. He calls the mind's ability to do this conversion the horizontal fundamental.
Horizontal. Why horizontal?
As opposed to the vertical fundamental, which is the usual reductionist digging downwards brain to neurons, to molecules, to atoms, to quarks.
Ah, okay. Horizontal is the mind's translation process. Vertical is the reductionist hierarchy.
Right. And Singh suggests that as we go deeper down the vertical path, the distinction between things and laws gets blurrier and blurrier.
Until maybe at the very bottom.
They become the same thing. An electron is both a thing, particle, and a manifestation of laws. Quantum field theory rules.
That's a deep thought. He also talks about evolution, right?
He does. He traces the history of neural components from simple ion channels in bacteria billions of years ago all the way up to our complex neocortex. It highlights this continuity, the same basic physical mechanisms repurposed and elaborated over eons to create thought.
It's humbling. So how does this thing law idea deal with subjectivity versus objectivity? Like, my thoughts feel personal, but math feels universal.
Singh tackles this head-on. He boldly proposes that this difference is basically an illusion. A law is also a thing. Mathematics isn't just in our heads, it's somehow also in the structure of the external world. Our neural pathways just mirror or represent these external thing law associations.
So the Pythagorean theorem exists both as a pattern in my brain and somehow out there in reality.
That's the suggestion. He acknowledges it's hard to literally see the proof of a theorem etched into a rock in our complex emergent universe. But at a fundamental level, he believes laws and things are intrinsically linked both within us and outside us.
And he has this idea about consciousness itself.
Yeah, really intriguing one. What if consciousness is the law aspect of this duality and the body, the brain's connectome, is the thing aspect?
Consciousness as the intangible law governing the tangible thing of the body.
It's a really poetic way to frame the mind-body problem.
Okay, let's shift to Sabine Hassenfelder. She brings a very pragmatic physicist's perspective, focusing on the limits of theories.
Right. Her key point is that physical theories aren't descriptions of ultimate reality. They are models that work at a certain resolution, a certain level of detail.
Like a map. A map with a certain scale is useful, but it's not the territory itself.
Exactly. And a crucial point. Nature doesn't allow mathematical contradictions. So if you have two different-looking theories that are both supposed to be valid at the same resolution...
They must actually be describing the same physics. They have to be physically equivalent, even if the math looks different.
Precisely. There can't be two conflicting truths at the same level of detail.
Okay, that makes sense. And she talks about emergence and reductionism, too.
She does. She discusses strong emergence, that more is different idea again, but in a really radical sense where the behavior of complex systems is in principle impossible to predict just from the parts.
Which would be a big problem for reductionism, the idea that everything can ultimately be reduced to fundamental physics.
A huge problem. But Hassenfelder explains why most physicists tend to lean towards reductionism, citing things like the causal exclusion argument.
which basically says if physics is causally complete, there's no room for non-physical things to have causal effects.
Right. And also the incredible success of effective field theories.
Oh, explain those briefly.
Effective field theories are like approximations. They let us accurately describe physics at lower energies or larger scales by essentially ignoring the super high energy details of a more fundamental theory. We can derive the low-resolution theory from the high-resolution one.
Which seems to support reductionism. The low-level stuff comes from the high-level stuff.
It does, but Hassenfelder points out a crucial loophole, a potential crack in the reductionist argument.
What's the loophole?
We don't actually know for sure if the equations of these effective theories can always be smoothly calculated or analytically continued, all the way from the highest resolutions down to the lowest ones. Meaning it's possible that at certain points you might need new information, new initial values that aren't contained in the higher resolution theory. You'd need to measure them experimentally.
Which would open the door for strong emergence, for genuinely new phenomena to appear that weren't predictable from the bottom up.
Exactly. It's a subtle but important point. Reductionism isn't quite mathematically guaranteed, even if it works incredibly well most of the time.
Okay, so limits and resolutions are key there. Now, Sean Carroll and Ashmeet Singh offer a very specific candidate for what is fundamental, right?
Yeah.
A minimalist quantum view.
Yeah, they push the quantum description to its bare essentials. They argue the most fundamental description of the universe might just need three things.
Okay, what are they?
1, Hilbert space. This vast, abstract mathematical space that holds all possible quantum states. 2, a state vector. A single point or arrow in that Hilbert space representing the entire current state of the universe.
The wave function of the universe, basically.
Exactly. And 3, a Hamiltonian. That's the operator, the mathematical rule that dictates how that state vector moves and evolves within Hilbert space over time.
And this is basically the framework of the Everett or many worlds interpretation.
It is. Their approach, which they cheekily call mad dog Everettianism, takes it to the extreme.
How extreme?
They argue that even things we think of as fundamental, like space itself or particles existing at specific locations, aren't needed at the absolute base level.
Wait, no space? How does that work?
They propose that space, locality, fields, all that familiar classical stuff actually emerges from this purely quantum description.
Emerges from just the state vector and the Hamiltonian in Hilbert space.
That's the idea. The truly fundamental ingredients are just the properties of the Hamiltonian, like its possible energy values, its spectrum, and the specific components of that state vector. Everything else is emergent structure.
How could space emerge?
They suggest it might arise from the entanglement structure of the quantum state. If nearby regions of space correspond to quantum degrees of freedom that are highly entangled with each other, while distant regions are less entangled, you might get something that looks like our familiar spatial geometry. They talk about redundancy-constrained states.
Okay, that's deeply abstract.
It is, and they acknowledge there are huge challenges, like how do you get the specific rules of our space-time, local Lorentz invariance, to emerge from a potentially finite-dimensional Hilbert space? It's an active area of research.
But the goal is ultimate minimalism, just quantum states and rules.
Quantum mechanics all the way down.
All right. Now, Ian T. Durham brings in Bell's idea of beebles. What are those again?
John Bell, of Bell's theorem fame, was dissatisfied with quantum mechanics, just talking about measurement outcomes. He wanted theories to talk about what is objectively real, independent of observation. He called these objectively existing things beebles.
Things that are as opposed to merely what is observed. Okay.
So Durham applies this idea to the concept of the universe itself. Can we think of the entire universe as a beeble? And if so, is it fundamental?
That seems like a reasonable question.
But Durham points out it's actually tricky. First, how do you even define universe? Especially with ideas like multiverses floating around. What does totality or existence even mean in that context?
Good point. And you can't just define it by what we can measure.
Because beebles are supposed to be the underlying reality from which measurements are built. So operational definitions don't work for beebles.
So what's the problem with the universe as a beeble?
Durham argues that when you try to define a universe as a beeble within a specific theory, say, the wave function of the universe in quantum cosmology, that definition usually has to refer to something else.
Like what?
like the specific configuration of fields or particles that the wave function is describing. The wave function isn't just floating free, it's a function of something else.
So the universe beable seems to depend on or be constructed from other more basic elements or structures within the theory.
That's his argument. A universe without any structure, without constituent elements, is basically meaningless. So, the universe conceived as a beable in this way isn't itself fundamental. It's built from something more basic.
Interesting. So the totality isn't the starting point.
Not according to this line of reasoning.
Okay, Gregory Anderi then brings us back to emergence, but with a focus on explanation.
Yeah, he challenges that built-in reductionist bias. We often see this tendency to label things as either fundamental or merely emergent, as if emergent means less real or less important.
He thinks emergent phenomena need their own kind of fundamental explanation.
Exactly. When genuine novelty arises in complex systems, things you couldn't predict just from the low-level rules, he argues that requires new fundamental explanatory structures that weren't present in the simpler constituents.
Can you give an example?
He uses classical dynamics, Newton's laws. Incredibly powerful, fundamental within its domain. It explains so much.
But we know it's not the most fundamental theory. It emerges from quantum mechanics or statistical mechanics.
Right. So Derry suggests we think about a hierarchy of quasi-fundamental explanatory structures. Each theory is fundamental for its own level of description and the phenomena it explains well.
So multiple levels of fundamentality, depending on the context and the questions you're asking.
That's the picture he paints.
Yeah.
He's optimistic we might reach a very deep level of understanding eventually, but he also suspects new mysteries will always pop up.
Making the journey more important than the destination.
Kind of, yeah. The ongoing process of understanding is maybe what really matters.
That's a nice thought. Now, Catherine Crowther looks at the conditions we'd expect a truly fundamental theory to meet.
Right. She comes from high-energy physics, where the traditional view is this ladder of effective field theories, hopefully leading down to one ultimate theory at the shortest distances, the highest energies.
The theory at the Planck scale, maybe?
Maybe. But she expresses some skepticism about claims made in principle. Like, just because a theory could in principle explain everything doesn't mean it does, or that we know it's the right one.
And she raises an epistemic worry, the knowledge problem.
Yes. Even if we had a theory predicting things perfectly at, say, the Planck scale, how could we ever be sure it's correct without actually doing experiments at those insane energies? Which seems practically impossible.
We can't build a Planck scale collider.
Not anytime soon. So there's always this gap between theory and potential verification at the supposed fundamental scale. She uses string theory as a key example.
String theory is often touted as a candidate fundamental theory, right? It's supposed to be UV complete, meaning it avoids infinities at high energies, and it has a minimal length scale built in.
It does. But Crowther points out that even if string theory is correct, its UV completeness doesn't magically solve the epistemic worry. We still can't directly test it at its fundamental scale.
And it might still just be an effective theory itself, an approximation of something even deeper.
That's a possibility. Plus, she notes that string theory, for all its mathematical elegance, doesn't currently tick all the boxes you might want for a final fundamental theory.
Like what?
Well, we mostly only understand it through approximations, perturbation theory. It seems to require a pre-existing background space-time to work, and it has this landscape of possible solutions, meaning its parameters aren't uniquely determined by the theory itself. It doesn't give us the universe, but potentially countless universes.
So still very much a work in progress, even if it's a leading candidate.
Definitely. The conditions for calling something the fundamental theory are pretty stringent.
Okay, nearing the end here. Ken Wharton has a different take. Fundamentality is about non-randomness.
Yeah, this is a really interesting angle. He argues that truly fundamental explanations shouldn't rely on randomness, or what philosophers call principles of indifference, basically assuming all possibilities are equally likely unless you know otherwise.
Why not? Isn't statistical mechanics built on those kinds of assumptions?
It uses them, but Wharton argues the real explanatory work in thermodynamics, for instance, is done by the second law. Entropy increases, not by the underlying assumption that all microstates are equally probable. The law itself carries the explanatory weight.
Okay. And where does this become a problem?
The biggest problem, he argues, is explaining the very low entropy state of the early universe, the Big Bang. Why did the universe start out so incredibly ordered? Randomness doesn't explain that. It would predict a much more disordered, high entropy state as being far more likely.
Right. The past hypothesis Just assuming the universe started with low entropy explains why things are the way they are now, but it doesn't explain the hypothesis itself.
Exactly. It kicks the can down the road. Wharton proposes that we need fundamental boundary explanations. The initial conditions aren't just random. They are governed by some fundamental principle or law.
Like maybe the universe had to start in a smooth, simple, low entropy state for some reason.
That's the kind of explanation he thinks is needed. He argues these boundary conditions, explaining the edges of the universe in time, should be considered just as fundamental as the dynamical laws that govern its evolution moment by moment.
So laws and boundary conditions together make up the fundamental explanation.
That's his view. You can't just have the rules of the game. You need the starting position too and an explanation for it.
Makes sense. Okay, finally, we have Ulla and Dworkesh offering philosophical and linguistic wrap-ups.
Right. Mozibur Ulla presents this lovely Socratic dialogue. Socrates discusses atomism, Leucippus, and Democritus, and contrasts substance, the stuff, and law, the rules, as potential candidates for what's fundamental.
And he uses a metaphor.
A beautiful one. Geometry and number as two complementary aspects of some deeper fundamental unity. It echoes some of the duality ideas we heard earlier.
Nice. And Aditya Dworkesh focuses on the word itself. Fundamentality.
Exactly. He does this sharp linguistic analysis, emphasizing that the meaning of fundamental totally depends on the theory you're using it within.
What's fundamental to a biologist isn't what's fundamental to a particle physicist.
Precisely. The connotations change because the underlying theoretical framework changes. Clear communication requires understanding which theory someone is implicitly using when they call something fundamental.
So how does he define fundamental within a theory?
He suggests something is fundamental to a theory if it's indispensable. You absolutely need it for a complete explanation of that theory.
Like the axioms in mathematics.
Kind of. He argues any theory can be reduced to a set of interdependent fundamental entities, concepts, objects, laws that are essential for its full description within that context.
Okay, so it brings it back to context and indispensability within a framework.
A very clear way to think about it.
Wow. Okay, so as we wrap up this deep dive into what is fundamental, it is abundantly crystal clear that there is no single neat answer waiting for us.
Not even close. We haven't stumbled upon the ultimate building block or the final equation.
No, instead we've journeyed through this incredibly rich, complex, sometimes contradictory landscape of ideas. Each one offers a unique lens, challenging our basic assumptions about how reality is structured.
Absolutely. We've heard compelling arguments against a single bottom layer, right? We've explored emergence, context dependence.
We've considered consciousness, maybe even the observer themselves, as potentially more fundamental than matter or space-time.
And looked at the very definition of explanation, the role of boundary conditions, the limits of our theories. It's been a whirlwind tour of foundational thinking.
A truly awe-inspiring intellectual adventure, honestly.
Which leaves us, and you, our listener, with maybe a crucial final thought to chew on. Given this incredible variety of perspectives, this lack of consensus, even among brilliant minds, what does this ongoing debate about fundamentality itself tell us about the very nature of science, about how we inquire into reality?
Does it show the limits of our current methods? Or maybe the richness of reality itself that allows for so many valid perspectives?
And how does this constant questioning, this evolution of what we consider fundamental, shape our ongoing quest to understand the universe and our place within it?
That is definitely something worth pondering long after this deep dive comes to an end. Thank you for joining us on this exploration.
Thanks, everyone. Until next time.